here in part 2, we're going to look at applying the idea of Riemann sums to some tables of data. In the first one, a car comes to a stop 5 seconds after the driver slams on the brakes. While the brakes are on, the following velocities are recorded to estimate the total distance the car took to stop. And so something to notice about this table, if we were to plot these points, our x-axis would be time and our y-axis would be velocities. And so let me just plot those points. So here's 0, 88, here's 160, here is 240, here is 325, 410, and 50. Right, so there's some data. And notice that this area under the curve would be equal to the width times the height. And so in this case it would be a velocity times a time. And so if we pay attention to some units here, the velocity is in feet per second and the time is in seconds. And so a velocity times a time gives you just feet. And so that's one way that makes sense of why the area under this curve represents distance, or more specifically total distance. And by total, what we really mean in all cases is net, the net distance traveled, although sometimes it ends up being gross as well. And that distinction will get clearer as we move forward. But if I wanted to come up with an approximation for the distance, I would just need to find a sense of the area underneath this curve. And I'm not told how I want to do that, and so I'm just going to choose to use a LRAM for this one, just because there's no expectation on how I do it. I do know that this is going to be an overestimate, because when a function is decreasing, an LRAM is always an overestimate. I'll sketch in my rectangles in red to help me see it. So there's my first rectangle, and my second rectangle, and my third rectangle, and my fourth rectangle. So I can see why it's going to be an overestimate. The width of my 4 rectangles is all 1. So they are the same width, which means I can use distribution. And the height at each spot in this case would be 88 plus 60 plus 40 plus 25. And I actually have a 5th rectangle here. So let me draw it a little bigger. It goes all the way to 6. All the way to 5. So there's my 5th rectangle, and it has a height of 10. So my overestimate on this case ends up having a value of 223, and in this case would be total feet traveled. And a good habit to get into is explaining it this way, because what this represents is the distance traveled from time t equals 0 to 5 seconds is about 223 feet. Right, so that would be an explanation of exactly what this is. Right, it's an estimation from that specific time, and it would be different if we were looking at different times or even use a different method. Let's consider a second example. In this one, we jump out of an airplane, and before the parachute opens, you fall faster and faster. your acceleration decreases as you fall because of air resistance. The table below gives your acceleration after t seconds. We want to estimate the velocity after 5 seconds. So again, if we consider this just graphically, if this is acceleration and this is time, and our curve has this type of decrease to it over time, then the area under the curve, if we think about the units in terms of length times width, would be meters per second squared for the height times seconds for the width, and when you multiply those two things together, you're left with meters per second, which is why the area under the curve represents total change in velocity. So my velocity when I first jump is 0. And my velocity at the end is, well, my new velocity is how much I've accelerated in total. So in this case, if I want to approximate this, I'm going to use a right Riemann sum. I'll do it in blue. And my right Riemann sum, since this function is decreasing, will be an underestimate, because my rectangles will always be under the curve. So my first rectangle here at 1 and 8.03. So let me sketch all this data in first. So there's a rough approximation of all my rectangles. Again, these rectangles each have a width of 1, and what's changing is their heights over time. So my heights are 8.03, 6.53, 5.38, 4.41, and for my fifth rectangle 3.61. So this gives me a total change in velocity of 27.96 meters per second. And some may argue that my velocity should be negative because I'm going down, right? Others may say that I am traveling down at the velocity of 27.96 meters per second, but I would need to give some type of indication of direction with velocity. And this is at t equals 5 seconds. And for our final example, we've got a few different things that are being asked of us. There's a golf course. We want to estimate the area of the green. The caretaker draws parallel lines 10 feet apart and then measures the width of the green along that line. Determine how many square feet of sod must be purchased to cover the green. So, if the guy's being lazy and is using midpoints to calculate the area, well, the thing to notice if he's doing that is that the reason he's being lazy is because there's just less rectangles. The midpoints of all my rectangles would have to be here at 28, and then at 62, and then at 55, and then at 30. So the reason it's lazy is because he's using only 4 rectangles. Just based on the data I have, I could only have those as midpoints. And that would be different from a left and a right and a trapezoid in this case. This would be 4 subintervals. Some may say you could do a lot of rectangles and do one here at 28, and then here at 50 and at 62, because each of those numbers is in the middle of something, and that's true. But I think if he's being lazy, then he's just using less rectangles, so he's gonna have a very accurate estimation. So if we're going to do a midpoint approximation for the first one, we need to notice a couple things. So let's assume he's only using 4 subintervals. So the MRAM each of those 4 rectangles will be 20 feet apart, so that'll be their width, and the midpoint at all 4 places will be 28 and 62 and 55 and 30. And so his approximation would be an area of 3,500 square feet. Now if he uses left rectangles, he'll have a lot more rectangles. And so each of his rectangles will be a width of 10, and he can use every left-hand side. So starting at 0 and going all the way. Oops, skip some. 50 plus 62 plus 60 plus 55 plus 51 plus 30, and he's not going to use 3 because that would be on the right hand side of that last rectangle. And so if he uses this method, then his approximation is 3,360 square feet. And if he uses a right rectangle method, then the width of each rectangle will still be 10, and he'll be using all of the same numbers as the LRAM, except he won't be using 0 and he'll instead be using 3. And notice that we're still showing our work. And when we calculate our approximation in this way, we end up with 3,390 square feet. And finally, we need to use trapezoids. So we really need to pay attention to what's happening with the trapezoid method. But again, all of our rectangles will have or trapezoids will have a width of 10. So then the average of the bases will have 0 plus 28 over 2 plus 28 plus 50 over 2 plus 50 plus 62 over 2 plus 62 plus 60 over 2 plus 60 plus 55 over 2 plus 55 plus 51 over 2 plus 51 plus 30 over 2 plus 30 plus 3 over 2. And our trapezoid approximation ends up being 3,375 square feet. So again, we're just using all these methods in a variety of ways. Hope this helps.